Hello everyone, my name is Min Tram. I am with the Department of Computer Science at the University of Texas at Arlington, and today I am presenting intuitive robot integration via virtual reality workspaces. For this presentation, I will cover background and motivation behind our current work, which includes some related work under the same scope of leveraging virtual reality for robotic research, our current contribution, a brief summary of our current implementation, and show you several demonstrations of our evaluation use cases. The motivation behind our work is the need for a high throughput, low downtime autonomous workforce to keep up with industrial demands. A good example of such a demand is during the COVID-19 pandemic, when shortages of essential goods are caused by the human workforce being interrupted by the disease. In such a scenario, a robot workforce is the ideal replacement for the missing human workforce. However, the process of acquiring a new robotic system or adding more robots to existing ones is difficult. Such a process often comes with an investment cost, followed by a long, tedious, and expensive process to integrate into existing work environment with no promise of performance improvement or profit. To address those issues, we propose a virtual reality robotic workspace that allows immersive exploration and effective assessment of robotic system integration. Now, the use of virtual reality to enhance robotics operations and research is not new. Several other existing works covers other domains of application, such as teleoperation, digital twins, and data collection for machine learning. However, those works share several key drawbacks. They rely on an existing robotic infrastructure, they often come with a cumbersome interface and interaction mechanism, and they only support single robot use cases. And so, in order to address those drawbacks and further enhancing capabilities, we have made the following contributions. We introduce a purely virtual robotic workspace with extensible robotic simulation for constructing, exploring, and programming robots in their desired environment. Our work eliminates the need to rely on physical systems, enable multiple robot collaboration, and provide an intuitive, informative, and organic user interface and interaction mechanism. We also purposely design our implementation to be flexible and adaptable so that we can extend our domain to several other industries such as training, education, and marketing. And here's a brief overview of our system with the communication pipeline on the figure. The VR site uses the Valve Index VR headset running Physics 4.0 under the hood with Unity to render and overlay interfaces to operate as well as relay operator interactions to simulate the robots. The robotic backend, and consequently the linkage to a physical robot, is entirely optional and is only needed for special cases such as inverse kinematics and collision avoidance planning. The robot backend is implemented in ROS1 with MoveIt and currently supports several models of Universal Robots E-Line, so for example UR10E, and Fetch Robotics Fetch Mobile Manipulator. And now we will demonstrate our evaluation use cases, which are training pick and place, a data collection for machine learning. We will also showcase simulation to reality transfer by running results in motion planning on real robot. We first demonstrate our ability to simulate multi-robot workspace with varying robot types and equipment configuration. In our virtual workspace, our method can simulate a variety of robot sensor configurations while maintaining proper hand-to-robot interaction. Each robot can be seen to actuate properly, maintaining the kinematic order and characteristics. Robot-to-robot interaction is also possible. We now demonstrate different workspace interaction models including free drive, ghost drive, and imitation. In free drive, the robot follows the operator hand guidance, allowing intuitive interaction and recording of organic motions. In Ghost Drive, the operator can specify end position without affecting the robot. Motion planning can then be delegated to MoveIt. Hand-guided free drive motion can then be recorded for other purposes. In our work, we examine the use case of recording joint trajectory for direct playback or input data for reinforcement learning algorithm. The trained dynamic movement primitives, or DMPs, were able to learn from our VR-produced data. Execution was evaluated on an identical physical robot. More information regarding DMPs in the paper. This is an example of record for playback, demonstrating a sample task of pick and place, guided by a human operator. That is the end of my presentation. Thank you for listening.